Hello, everybody. Happy Monday. So, know that tomorrow is a professional development day. It doesn't affect us because we meet Monday, Wednesdays. But if you have Tuesday classes, you shouldn't be meeting asynchronously or rather synchronously. So we're still chipping away at chapter. I don't know which chapter number it is, but it's chapter 6, no, chapter 7. Yeah, which is a big chapter. Lots of stuff in here. So we had been working on balancing equations. Now I want to talk about balancing an equation if there happens to be a polyatomic ion in it. So balancing with polyatomic ions. So here we've got magnesium chloride, and it's mixing with sodiums and what are those, phosphates. And when they all get mixed together, they can swap partners. So the magnesium could move with the phosphate and the sodium could mix with the chlorine to produce, hopefully, what we will end up seeing is a precipitate forming. In this case, the polyatomic ion is a little packet here and it remains a little packet over here. So we can balance those, sort of treating them as a single unit. So here is the equation. I'm gonna write this on another page. So we've got sodium phosphate and magnesium chloride, okay. So we have sodium phosphate, Na3PO4. The reason that there's a 3 here is because, remember, sodium has a plus, plus 1 charge, and phosphate, PO4, has a 3 minus charge, so it's getting flip-flopped. All right, so we've got Na3PO4 plus magnesium chloride, which was MgCl2. And they recombined to produce sodium chloride, NaCl, and magnesium phosphate, which would be Mg3PO4. Okay, so when we're balancing this, I've got sodium, I've got magnesium, I've got chlorine, and then I've got phosphorus and oxygen. But if you notice, the phosphorus and oxygen stay grouped as a polyatomic ion, right? They don't separate, the oxygen doesn't like come off as a gas, so they're staying compact. So I'm gonna take inventory of them as a sole unit. Now I can't do that if it happened to break up. Let's say it was PO4 here and over here it's PO3 and then there's like oxygen gas coming off. We couldn't do that. But instead of taking phosphorus and oxygen separately, if I don't have to, I'm just going to treat it as a unit. So on this side, I have 3 sodiums, I have 1 magnesium, I have 2 chlorines, and then I have just 1 phosphorus, or rather phosphate ion. The 4 is included in the packet, so don't tell yourself you've got 4 of them. You've got 1 of those guys. On the other side, I've got currently 1 sodium, 1 chlorine, 3 magnesium, that's a 3, sorry. And then phosphate is in parentheses, and there's a 2 on the outside of it. So it's telling me that I have 2 phosphate ions. I like this because some things are 3s and some things are 2s. So I'm thinking we can make this work. All right, so metals before nonmetals. So sodium, there's 3 over here. I don't want to do sodium yet. Magnesium. Okay, magnesium, there is 3 over here And there is only 1 over here. So I'm going to put a 3 here. That changes this to 3, changes my chlorine to 6. So I could put a 3 here, but I already can see that I need 6 chlorines. So instead of a 3, I'm going to put a 6 in front of this. That gives this 6, that gives this 6. Now I can balance my sodium if I put a 2 here. That changes this to 6, and it changes this to 2. Everything is balanced. So when you can, right, treat the polyatomic as a whole unit instead of having to add up all the phosphoruses and add up all the oxygens. Just treat it as a unit and then take inventory from that. So let's have you do an example or two of a balanced equation with a polyatomic ion. So again, they take inventory of it together. Come on. Okay, so here's a couple. I want you to do A, B, and C. Just balance them out. Don't worry if it's 1, 2, 3, just put the coefficients. C is that situation where you do have a polyatomic ion in there. Okay, so the first two, there isn't a polyatomic, but that last one does have one. So go ahead and try and balance those guys out. We've got Fe2O3 plus C gives us Fe plus CO2. There are phases on there, but you don't have to worry too much about it. B is aluminum, Al plus FeO gives us Fe plus Al2O3. And then the last one is aluminum Al plus H2SO4 gives us Al2SO43 plus H2 gas. I'll give you all, it's 11:09. I'm going to give you until 11:15 to work through those. Anybody that's having trouble, ask me now, or if there's questions, ask me now while you have me available. I'd love to help you out. Otherwise, I'm going to throw my mute on so you don't have to hear me eating. Brooke, I'm not lecturing right now. I'm just having you all work on A, B, and C. So that might be why you aren't hearing anything, because I'm not talking. Okay, so let's look at these. So the first one is we have iron and iron oxide mixing with carbon to produce iron and CO2. Yeah, okay. So we've got iron, oxygen, and carbon, 2 irons, 3 oxygens, and 1 carbon, 1 iron, 2 oxygens, and 1 carbon. Rewind that, 2 carbons. Nope, 1 carbon, 1 carbon. There we go. Okay, it's 1. All right, I'm gonna leave carbon to the end. There's 2 irons here. We're in that odd even thing again, so there's nothing I can put in front of here that's going to give me a value of 3. So I'm going to balance that out. If I put a 2 here, that will change this to 4. It'll change this to 6. That's all right, because then I can put a 3 here, which will change this to 6 and this to 3. Then I can just finish that off by putting a 3 there and a 4 here. 2, 3, 4, and 3. Any questions on that? Is that matching up what you guys got? Pull up another one. Aluminum with iron oxide. Okay. So we've got aluminum, and it's combining with an iron oxide to produce iron and aluminum oxide 2, 3. So here I've got aluminum, iron, and oxygen. 1, 2, 1, 1, 1, 3. So for this one, I could just put a 3 in front of here. That changes this to 3. It also changes this to 3. Put a 3 in front of here, changes this to 3, and then I put a 2 in front of there to make that 2. So we're balanced. Now the last one was the one with the polyatomic ion. We had aluminum plus aluminum plus H2SO4 produced, it was hydrogen gas plus aluminum sulfate. Okay, they have these 2 flipped, but it's the same thing. So in this one, we have aluminum, hydrogen, and I've got sulfate, but it stays sulfate on this side. We just have a multiplier of it. So I'm going to keep that as SO4. 1 aluminum, 2 aluminums, 2 hydrogens, 1 sulfate, and over here I've got three sulfates. So the sulfates need to get balanced. I mean, I guess we could balance aluminum 2 if we wanted, so I could put a 2 there. Change that. The sulfates, I'm going to put a 3 here. That'll change this to 3. It'll change this to 6 because we take this number, multiply it by this number. Remember, when you're taking this 3, it distributes to both things, and this is, that's a whole chunk, okay? To finish it up, let's stick a 3 here, and that will change this to 6, and we're balanced, balanced, balanced. Could you have done it where you take S's and O's separately? You can, but if there's a polyatomic, I just recommend doing it clumped like that. Okay, so let's start going into the different types of chemical reactions. So and a lot of times chemical reactions will fall into predictable, definite description. So here we've got candles burning, and that's a combustion reaction. So here are the different types of chemical reactions we're going to go over: combination reactions, decomposition reactions, single replacement reactions. Sometimes this is called single displacement reactions. It means the same thing. Double replacement reactions are sometimes again called double displacement reactions. And then we have combustion reactions. So we'll look at some examples of each of those. Okay, in a combination reaction, 2 or more elements form one product. So we have A and B, and they get together to form AB. So these are all examples of combination reactions. Magnesium combines with oxygen to produce magnesium oxide. Sodium combines with chlorine to produce sodium chloride. In this case, we have sulfur trioxide. This is not the sulfite ion because there's no charge. So sulfur trioxide combines with water to produce H2SO4 or sulfuric acid. I'm going to give you 2 elements, and I want you to write a balanced combustion, a balanced combination reaction. Okay, I'm just going to give you the reactants. You've got to tell me what the product is, and you need to balance it. Come on, there we go. So let's say we have aluminum combines with sulfur. I want you to write the combination product and balance it. So if aluminum and sulfur are going to come together, they're going to come together to form what? Whew. Real quick, show you again here. So separated, brought together in a balanced way. Separated, brought together. Okay, so for this, if I tell you, hey, aluminum and sulfur come together in a combination reaction, you would need to write a product where these 2 things come together. Now this is a metal and this is a non-metal. So in order to write a product for this, you would need to balance charges. Remember, aluminum has a 3+ charge, sulfur has a 2-. So I'm going to flip-flop these to become Al2S3. It's not enough to just be like, oh, I'm just going to smush them together, ALS. We've got to make sure that we're charge balancing. From there, take inventory, aluminum, sulfur, 1 aluminum, 2 aluminums, 1 sulfur, 3 sulfurs. This should be pretty easy to balance. We just throw a 2 here and a 3 here, and we're balanced. I'll give you one more. Let's write a combination reaction for, what do I want to do? Calcium combines with phosphorus. Okay, so in this situation, we've got calcium, and it's a solid, combines with phosphorus, and say it's a solid. Neither of those are diatomic, so I'm not going to put a 2. And we're going to produce, well, it's combination. So I've got calcium combined with phosphorus. Calcium has a 2+ charge. Phosphorus has a 3- charge. So I need to flip flop, and we get Ca3 PO. Why am I going for PO? Let's go for P2. Then if we want to balance this, calcium and phosphorus, 1, 1, 3, 2, and just throw some coefficients here to balance it out. So I think combination is sort of the easiest one to understand. Let's look at, okay, so here we've got a magnesium ribbon, and you burn it with oxygen coming from the air, and it glows this really, really bright color, or this bright white light. And then you end up with magnesium oxide. So your final product actually is heavier than your original product, and it has little oxygens inserted in there. The next type of reaction we're going to classify as a decomposition reaction. So in a decomposition reaction, one substance will split into 2 or more simpler substances. So we have a couple, and they break up into their individual components. Here we've got mercury oxide, and it breaks up into mercury and oxygen. Here I've got potassium chlorate, and it breaks up into potassium chloride and oxygen. This is a little bit more complicated than what I would expect you guys to know. So I'm not going to give you something like this and say, hey, what does it break up into, and have you know that the oxygens are going to separate, but the chlorine isn't going to separate. We're not going to get that far into it. But you do need to be able to identify, okay, that it's a decomposition reaction. So you need to be able to look and say, this is decomposition. Here we've got mercury 2 oxide, and it breaks up into mercury, and oxygen comes off of it if it says. Okay, the next type is a single replacement reaction, or sometimes it's called single displacement. So in this situation, we have A plus BC. So BC is already a couple. A is more appetizing than B in this situation. So what will happen is Z will switch partners, or C will move over to A. So we end up with AC and then B gets booted from the relationship. So we can see here zinc is the reactant coming in by itself, and there's hydrochloric acid. And the chlorine has a stronger affiliation for the zinc, so it's going to attach to the zinc and spit out the hydrogen gas. Same thing here, we've got iron and then copper sulfate, copper 2 sulfate. The sulfate has a stronger affinity for the iron than it does for the copper. So it's like, sorry, copper, you were so last year, I'm going to get with iron and you can just hang out. So again, this is something that you're going to want to be able to identify. Here's a real life example. So we take zinc and we put it in hydrochloric acid. If you've ever watched like a James Bond movie or anything like that, where they melt, or not melt, but they dissolve metal with acid, this is what's happening. So we've got hydrochloric acid. We put it in with the zinc, or we put it on the zinc, and it swaps the chlorine, or rather it swaps the hydrogen with the zinc. And now the zinc that was originally a solid has become an aqueous solution where it can dissolve. Then we have double replacement or double displacement reactions. This is where we have one couple here and we have another couple here, and they're going to swap partners. But they're going to do it by still honoring metal, non-metal interactions. So A is the metal in this situation, B is the non-metal. We're not going to have the metal from one go with the metal from the second. Okay, we're going to have the metal from the first one go with the non-metal from the second, and vice versa. The metal from the second is going to go with the non-metal from the first. So here I've got my metal and my non-metal, my metal and my non-metal. Over here we've got a metal and a non-metal, a metal and a non-metal. So we're still keeping it metal, non-metal combination. So I could give you these and say, hey, what are the potential products? And you would be able to write the products because you're going to flip-flop partners in that way. So here's an example. We've got sodium sulfate combines with barium chloride to produce barium sulfate and sodium chloride. What's happening in here is these guys are aqueous, and these are also aqueous. So they're sort of floating around in solution. They're not actually bumped into each other. They've dissociated from each other. And so there's this sort of party. It's like you can think when they're aqueous that they've all had a little bit too much to drink, right? So they're all sort of separating from their partners. And what happens is when we mix them together, partner from here combines with partner from another couple. And sometimes they find that the new partnering, like with barium here and sulfate here, that actually will produce a solid. And then you'll get a precipitate coming out of solution. So if you ever have two liquids and you're pouring them together and all of a sudden a solid forms, that's what's happening. So I'm going to give you one of these. I want you to write the potential products. And I want you to balance the equation, okay? So what do I want to do? Calcium. Hold on. I had one in my head and then I lost it. I'm going to say calcium nitrate combines with lithium phosphate. Lithium phosphate. You don't need parentheses. Okay, I want you to write the products. We want to do some flip-flopping, and I want you to balance it as well. I'll give you a little help. This is behaving as a metal. This is behaving as a metal. The polyatomic is behaving as the non-metal. When you write your two products, though, make sure they're charge balanced before you go ahead and balance the equation. So with this one, I gave you the first part and you've got to figure out what the potential products are. And I would say, hey, this is a double displacement reaction. So you're going to take the metal from the first one and combine it with the non-metal from the second. So that's going to be calcium phosphate. Now calcium has a 2+ charge and phosphate has a 3- charge. So I have to take that into account. So calcium is going to get the 3. The phosphate is going to get the 2. Now, we're going to combine the nitrate and the lithium. What I see happen all the time is students will be like, but there's 3 here and there's 2 of them here, so that needs to transfer over. Well, no, the first thing I do is just make sure that the formulas I'm writing are correctly charge neutral. So sodium has a +1 charge. Nitrate also has a -1 charge, so it's a 1-to-1 ratio. So I'm going to write this as LiNO3. Now I get it. There are 3 lithiums here and there's only 1 lithium here. I'm going to fix that by then changing the coefficients. So I have lithium, I have calcium, I have nitrate, and I have phosphate. Now remember, if their polyatomics stay intact, you can keep them as a whole. Lithium on this side, I got 3, calcium 1, nitrate 2, phosphate 1, calcium 3, phosphate 2, lithium 1, nitrate 1. Okay. So what do I want to do first? Guess I can do calcium. I'm gonna leave lithium. So calcium, I've got 3 here. So I'm gonna put a 3 here. My pen will work for me. 3. So that changes calcium to 3, but it also changes my nitrate. My nitrate is now gonna become 6. I had 2, we put a 3 in front of it, we get 6. So I can balance out the nitrate. If I've got 6 on this side, I need to have 6 on this side. So I'm gonna put a 6 there. That's going to change this to 6, and know that you can balance in slightly different ways. You can balance certain things before other things. That happens. That changes my nitrate to 6. It also changes my lithium to 6. So we can balance lithium by putting a 2 here. That will change this to 6, and it changes my phosphate to 2, which makes everything balanced. So I think the balancing usually isn't the problem for people. Oh, excuse me. The balancing isn't usually the problem. It's in combining them isn't even the problem. It's that you're not using the charges to write the correct formula first. So the first thing you want to do is get the right formulas, then balance in front of it. Don't say, oh, well, there's 3 here, so I need to put a 3 there. No, lithium and nitrate will only come together in a 1-to-1. Do I have any questions on that? Okay, move on. So the final reaction that you need to be able to identify is a combustion reaction. You're thinking, oh, combustion, like when you drive your car or your grill. That is exactly what we're talking about. So you take some sort of carbon-containing compound, you burn it with oxygen gas, and you're always going to form CO2 and H2O. And then obviously you form energy or heat as well until we cook our food and run our car. So I could give you whatever the hydrocarbon is, and you would be able to write a formula, and you'd also be able to balance it, because you know that in order for a combustion reaction to occur, your hydrocarbon has to combine with oxygen to produce CO2 and H2O. Those are your products. Has to combine with oxygen. Same here. We've got C3H8 combining with 5 O2s to give us 3. Again, the base though is that it's CO2 and water plus energy. So let's say, I want you to do one of these. Give me just 1 second. So I'm going to have you write a complete balanced equation for, so write balanced equation for the combustion of hexane. Now, at some point, you will know what hexane is later on in the semester. You will get to learn all that nomenclature. It'll make nomenclature for inorganic seem simple. So hexane is going to be C6, hence the hex, H14. Okay, so all I'm giving you is the hexane, but I want you to write the full combustion equation. Now, and balancing this one can be a little tricky, so just give it a try. No worries, Ashley. We'll see you next time. Okay, so hexane. C6H14. We're going to combust it. So that means I have to combine it with oxygen. And oxygen is O2 because it's a diatomic. And this is going to produce CO2 and H2O. So I've got carbon, hydrogen, and oxygen. I'm going to balance my carbons first. So I've got 6 carbons there. So I'm going to throw a 6 here. Oh, you know what? Let me take inventory first. Okay, I've got 6 carbons, 1 carbon, 14, 2, 2, and 3. As you start to get better at them, you don't necessarily have to take inventory. You may start to see some patterns, but okay, so carbon, I'm gonna put a 6 here, 6. Hydrogen, I've got 14 here, and I've only got 2 there, so I'm gonna put a 7 there. This is totally wonked up my oxygens. So I have 2 oxygens times 6 gives me 12 oxygens there, plus 7 oxygens here is 19 oxygens. Okay, I'm gonna show you a little trick on what you can do if you have this odd even thing. If I have 19 oxygens here, I need to get to 19 oxygens here. So what I can do is put 19 over 2. Because if I take 19 divided by 2 times 2, the 2's will cancel and I'll be left with 19. Can we have half coefficients? No. So to get rid of this, I'm just going to multiply everything by 2. So I'm going to multiply this whole thing by 2. What's that going to do to this? It's going to make this a 2. What will happen here? It'll make it 19. This will become 12. And this will become 14. Let's count up. So that's 12 carbons there. That's 12 carbons there. That is 28 hydrogens, boy, and 14 times 2 is also 28. Oxygens, 19 times 2 is 30, 38. No, 30. I am not good with basic math. I have a minor in mathematics, but my brain cannot hold 38 basic math anymore. Yeah. Okay, 38. And then over here, we've got 14 oxygens. Okay, because it's by 7. That distributes out, plus 12 times 2, that is going to be 24. So 24 plus the 14 does in fact give us the 38, and we're balanced. Sometimes they can be really big like that. But the 2 there is a little trick to balance out a little faster. All right. So here are the different types of reactions and some sort of example of them: combination, decomposition, single, double, and combustion. So looking at these, I want you to identify them as combination, decomposition, single replacement, double displacement, or a combustion reaction. So when looking at this, we've got this first one here. We've got aluminum by itself, and then we've got hydrogen and sulfate combined. And then what we end up happening with our products is that the aluminum takes the place of the hydrogen. So this I'm going to go with a single displacement. The second one here, I've got sodium and sulfate combined with silver and nitrate, and it becomes silver sulfate and sodium nitrate. Here they flip-flop partners. So this would be a double displacement. This next one here, I've got carbon combining with an iron oxide. Iron gets booted and we end up with carbon. So this would be another single displacement. And then this last one here, carbon and oxygen producing CO2 and H2O in some fashion. That's going to be a combustion. We didn't even have this one, so I don't know where that came from. But if this one was available to us as our C value, right? I'm not going crazy. Yeah, no, that was not the C. If we were to look at this one, we've got A plus B becomes AB. That would be a combination. Okay, I'll give you 1 minute to go through these and classify what you would think them as. You don't even have to write them down. Just get in the habit of what are those. Okay, first one, definitely combination. Second one, we're booting hydrogen. So this would be a single displacement or replacement. Here we've got a hydrocarbon of some kind mixing with oxygen to produce CO2 and H2O. That's our classic combustion. Metal, non-metal, metal, non-metal, and we flip-floppies. So this is a double. And then this thing is decomposition. We had a unit and now we've broken into two. Oxidation and reduction reactions. So when we get something like rust, that is happening when iron reacts with the oxygen in the air. In this case, there is a transfer of electrons from one substance to another. And we define the transfer of electrons as one thing being oxidized, one thing being reduced, depending on if it's gaining or losing an electron. So here's an oxidation reduction reaction. Some things provides energy for food, provides electrical energy as well, occurs with rusting. So we've got iron, combines with oxygen to produce an iron oxide. The thing that is here, yeah, there it is down there. So oil rig is one way to remember oxidation and reduction. An oil rig, oil is oxidation is loss of electrons. So the things that's being oxidized is losing electrons. Rig is reduction is gaining electrons. So if something's being reduced, it's going to gain an electron. So when looking at this here, we have substance A, and it has an electron that it doesn't particularly want. Over here, we've got substance B, and it wants the electron. So the electron is going to transfer from A to B. In this case, the thing that's losing the electrons is being oxidized, oil. The thing that's gaining the electron, B, is being reduced. And I know that's sort of weird sounding because when you think reduce, like you'd be thinking, oh, I'm reducing. Why am I gaining an electron? So just make note of that. If we look here, we've got copper. Ooh, that slide is kind of messy. No, I don't like that one. Okay, let's go. We can go here. So we've got zinc combining with copper, and the copper has a 2+ charge. And what ends up happening is that the copper takes 2 electrons from the zinc, or it sort of flip-flops places. So we can see here, here's our copper with the 2+. It comes in and it pops the zinc off. And when it pops the zinc off, the zinc transfers the electrons to the copper. So in this case, I can see that I have a zinc with, what is my charge here? Its overall charge is 0. On the other side, its overall charge is 2+. That means that it has lost 2 electrons. Okay, when we lose electrons, you can have Leo the lion goes grr, or oil rig. Loss of electrons is reduced. So the zinc is being reduced here. In this case, we've got, we've got our zinc, and then we've got our copper. So in this case, copper has a 2+ charge, and it becomes copper with a 0 charge. I believe I told you this wrong. Yeah, so zinc, I'm even confusing myself, so I'm gonna just write it out. So we've got zinc here. To go from this zinc to this zinc, it needs to lose 2 electrons. So we've got oil rig. So this thing is being oxidized because it's losing an electron. Here, or rather 2 electrons. I'm going from a 2+ charge to a neutral charge, which means that I've had to gain 2 electrons, so +2 electrons. So if we're gaining electrons, we're reducing. I don't know why these slides are so messy. Let me try and clean this up. Okay, so when looking at these equations, I want you to determine if it is oxidation or reduction. So in the equation is this material gaining or losing electrons? And then how does that relate to being oxidation or reduction? So for this first one here, we've got tin, and it is, okay, we've got tin, and it is losing 4 electrons, right? So it's going from what is normally a neutral charge, because we don't have a charge in the upper right-hand corner, to a 4+ charge, which means that it has lost 4 electrons. So again, we write out our oil rig. And if we're going to lose electrons, we're being oxidized. So this is an oxidation. In this case, we are gaining 1 electron. We're at a 3+, and we go to a 2+. So we gain 1 electron to increase our charge. So if we're gaining electrons, we're reducing. And then here, we're going from what is a 0 charge, no charge there. We're gaining 2 electrons to form a minus charge, but there's 2 of them, so -2 charge. So this would also be reduction. So looking at this equation, I want you to tell me what material in it is being oxidized and what material is being reduced. So we've got silver with a plus charge and chlorine with a minus charge. We put UV light on it and we get silver with a 0 charge and chlorine with a 0 charge. So I want you to tell me which of the two, the silver or the chlorine, is being oxidized and which of them is being reduced. Okay, so just to get this in, the way I kind of like to do these to determine which is being oxidized and reduced is I'll pair them off. So here's the silver and here's the silver. What happens in order for it to go from this to this? So it was a positive charge and now it's a neutral charge. It had to gain an electron to make that happen. So I'm going to put gain an electron. Oil rig. If I'm gaining an electron, I'm being reduced. So silver in this case is being reduced. Now, once you figure out which one's being silver, AG, once you figured out which one is being reduced, the other guy is being oxidized, but we can double check it. Here's our chlorine. We're gonna go over here. Here we're a minus charge and here we are a neutral charge. So what had to have happened was we had to, and in this case, we actually gained 2 electrons. We had to lose 2 electrons to make that happen. Loss is oxidized. So the chlorine, the Cl, is being oxidized. So pair them up, see which one's losing electrons, see which one's gaining electrons, and you'll get your answer on who's being reduced and who's being oxidized. Okay, we're not going to talk about that. Here's some things. So the particular definition of oxidation and reduction does depend on the process, but oxidation in general always involves a loss of electrons. May also be seen as an addition of oxygen. So sometimes instead of losing electrons, we're going to add oxygen because the oxygen is greedy for electrons, so it'll pull in the electrons, or it could be the loss of hydrogen. This will happen in a more biochemical sense when we're dealing with our biochemistry, so we may come back to this concept. The definition of reduction always involves a gain of electrons, may also be seen as a loss of oxygen or a gain of hydrogen. Hydrogen, again, having this sort of positive charge to it, oxygen having this negative charge to it. So if we're losing oxygen, which is negative, it would be the same thing. Let's see. Okay, so we're going to stop there. The last thing is going to be chemical quantities and reactions. So this is stoichiometry stuff. We're not going to spend a whole lot of time on it, just one lecture. And then your guys' test will be a week from yesterday and today. So let me know if you have any questions. Otherwise, we'll stop there. It's a nice day, so you can go out and vote if you haven't already. I personally know about 3 or 4 people who have never voted in their lives, some of them being in their 40s and 50s, who are voting for the first time ever. So if you haven't registered or you haven't voted, never a better time than right now.
I voted first day.
Yay! Yeah, so did I. I voted the first
One thing on time. Just kidding.
Yeah. So if you did vote, send me an email. Okay, let me know that happened. Otherwise, enjoy the rest of your day. Stay around if you have a question. Bye. Marilena, do you have a question?